Today's problem involves two friends, Alice and Bob, and their candy. They want to make a single swap to make their total candy amounts equal. Take a moment to think, what would you do to figure out which candies to swap? Alright, let's break down the fair candy swap problem. Imagine Alice has a collection of candy bars, and each bar has a specific size. Bob also has his own collection of candy bars, each with its own size. We're given these two collections as lists of numbers. For example, Alice might have candy bars of sizes 1 and 1. Bob might have candy bars of sizes 2 and 2. Our goal is to find one candy bar from Alice's collection and one candy bar from Bob's collection, such that if they swap these two specific candy bars, their total sum of candy sizes becomes exactly the same. We need to return the sizes of the two candy bars that should be swapped. It's guaranteed that such a swap always exists, and if there are multiple possible swaps, any valid pair will do. So, in our example, Alice has candies totaling 1 plus 1, which is 2. Bob has candies totaling 2 plus 2, which is 4. Their sums are currently 2 and 4. If Alice gives Bob her candy of size 1, and Bob gives Alice his candy of size 2, what happens? Alice's new total would be her original total, 2, minus the 1 she gave away, plus the 2 she received. So, 2 minus 1 plus 2 equals 3. Bob's new total would be his original total, 4 minus the 2 he gave away plus the 1 he received. So, 4 minus 2 plus 1 equals 3. Both their totals are now 3. So, the output for this example would be the pair 1 from Alice and 2 from Bob. What makes this tricky is that we have many possible pairs of candies to consider, especially when Alice and Bob have many candies. We can't just guess, we need a systematic way to find the right pair. The lists of candy sizes can be quite long, up to 10,000 candies each, and individual candy sizes can be large too, up to 100,000. This means we need an efficient way to search, otherwise, our solution might take too long to run. The most straightforward, or brute force approach, is to try every single possible combination of a candy from Alice and a candy from Bob. Here's how it would work. First, we need to know the total amount of candy Alice has and the total amount Bob has. So, we'd go through all of Alice's candies and add up their sizes to get Alice's total sum. We'd do the same for Bob to get Bob's total sum. Let's call these summa and sum b. Now, we start our search. We pick Alice's very first candy. Then, we go through all of Bob's candies one by one. For each of Bob's candies, we imagine swapping it with Alice's chosen candy. After each imaginary swap, we calculate Alice's new total and Bob's new total. Alice's new total would be summa, minus the candy she gives away, plus the candy she receives from Bob. Bob's new total would be sum b, minus the candy he gives away, plus the candy he receives from Alice. If these two new totals are equal, we've found our pair, and we can immediately return those two candy sizes. If not, we move to the next candy in Bob's list and try again with Alice's same candy. Once we've tried Alice's first candy with all of Bob's candies, we then move to Alice's second candy. We then repeat the entire process, trying Alice's second candy with every single one of Bob's candies, checking the sums each time. We continue this until we find a pair that works. Why is this slow? Because if Alice has n candies and Bob has m candies, we are essentially doing n rounds of checking, and in each round, we check m of Bob's candies. This means we perform roughly n multiplied by m checks. If both Alice and Bob have 10,000 candies, that's 10,000 multiplied by 10,000, which is 100 million checks. That's a lot of repeated calculations. The space complexity, however, is very good because we only need to store the sums and the current candies we're looking at, which is a constant amount of extra memory, regardless of how many candies there are. The key insight to optimize this problem is to transform the balancing condition into a simple equation that we can solve more directly. Instead of recalculating sums repeatedly, let's figure out exactly what kind of candy Bob needs to have for any given candy Alice might give up. Let's say Alice's total candy sum is summa, and Bob's is sum b. If Alice gives away a candy of size A and receives a candy of size B, her new total will be summa minus a plus b. Similarly, Bob's new total will be sum b minus b plus a. For them to be fair, these new totals must be equal. So, summa minus a plus b must equal sum b minus b plus a. We can rearrange this equation. If we add b to both sides and subtract a from both sides, we get summa minus sum b equals 2a minus 2b. This can be further simplified to summa minus sum b divided by 2 equals a minus b. Let's call this summa minus sum b divided by 2, the difference or diff. So, diff equals a minus b. This means for any candy that Alice offers, the candy b that Bob must offer must satisfy b equals a minus diff. This is the magic formula. Now, instead of trying every b for every we can just calculate the b we need and then quickly check if Bob actually has a candy of that size. To do this quickly, we first calculate the total summa and sum b for Alice and Bob just like before. Then we calculate our diff value. Next, we put all of Bob's candy sizes into a special data structure called a hash set. A hash set is like a super fast list that allows us to check if an item exists within it almost instantly, no matter how many items are there. It's much faster than searching through a regular list one by one. Once Bob's candies are in the hash set, we go through each of Alice's candies one by one. For each of Alice's candies, let's call its size current A. We calculate the target size that Bob must have for the swap to work. Using our formula, target equals current A minus diff. Then, we use our superfast hash set to ask, does Bob have a candy of this target size? If the answer is yes, then we found our pair. We return current A and target. If we go through all of Alice's candies and don't find a match, it means something went wrong. But the problem guarantees a solution always exists, so we will always find one. This approach is much faster because we only iterate through Alice's candies once. And for each of Alice's candies, we do a very quick lookup in Bob's hash set. The time complexity becomes proportional to the number of Alice's candies plus the number of Bob's candies, which is much better. The space complexity is now proportional to the number of Bob's candies, because we store all of them in the hash set. Let's trace our optimized algorithm with the example. Alice has candies of sizes 1 and 1. Bob has candies of sizes 2 and 2. First, we calculate Alice's total sum. We iterate through Alice's candies. 1 plus 1, so summa, becomes 2. Next, we calculate Bob's total sum. We iterate through Bob's candies. 2 plus 2, so sum B becomes 4. Now, we calculate the difference, or diff. Diff equals summa minus sum B divided by 2. So, diff equals 2 minus 4 divided by 2, which is negative 2 divided by 2. So, diff is negative 1. Our next step is to create a hash set and put all of Bob's candy sizes into it. Bob's candies are 2 and 2. So, our Bob set now contains 2. Even though there are 2 candies of size 2, a hash set only stores unique values, so it just contains the number 2 once. Now, we iterate through Alice's candies. Alice's first candy has a size of 1. Let's call this current A. So, current A is 1. We calculate the target candy size Bob needs. Target equals current A minus diff. So, target equals 1 minus negative 1. Remember, subtracting a negative is like adding, so target equals 1 plus 1, which is 2. We now check if our Bob set contains this target value 2. We ask, does Bob set contain 2? The answer is yes because we put 2 into the set earlier. Since we found a match, we immediately return the pair, current A, which is 1, and target, which is 2. And that's our result. And there's our final result. The pair of candies to swap is 1 from Alice and 2 from Bob. This swap makes both their total candy sums equal to 3, confirming our solution is correct. You'll often spot this pattern when you need to find a pair of elements from 2 different lists that satisfy a certain condition, especially if that condition can be rewritten as a simple equation. If you find yourself repeatedly searching one list for a specific value based on an element from another list, consider pre-processing one of the lists into a hash set or similar fast lookup structure. This is a common strategy to turn a slow, nested loop into a much faster single pass. Our optimized solution achieves a time complexity of O, n plus m, where n and m are the number of candies. The space complexity is O, m, due to storing Bob's candies in a hash set. Try the next problem that involves finding pairs or sums. You might find this hash set pattern useful again. If you found this explanation helpful, please consider subscribing for more DSA breakdowns.